Hello dear students, welcome to mathematics class. In this class, let us discuss the second case of the particular integral. So the first case is when the RHS of the differential equation is e power ax, and also we have discussed the case of failure, means when f of a is equal to 0, then how to solve the particular integral of that differential equation. And now here we are going to discuss the particular integral of the differential equation when RHS is of the form sin ax or cos ax. So first let us derive the formula for that one. So here particular integral when RHS is sin ax or cos ax. So for both the functions the particular integral will be same. So as in the previous case, by using the successive differentiation we are going to prove this. So 1 by f of d square sin ax equal to 1 divided by f of minus a square sin ax. So here observe this carefully. This is f of minus a square and this is not f of minus a whole square. So there is a difference between f of minus a square and minus a whole square. If it is minus a square means, so after squaring a number we need to apply the negative sign, and minus a whole square means first we need to apply the negative sign then square that will be again a positive quantity. So but here it is f of minus a square, means whenever the differential equation has RHS sin ax or cos ax, then just substitute d square equal to a square, means only the power of d should be a multiple of 2 or it is equal to 2, then only we can apply that d square as minus a square. Suppose it is d cube, then we cannot directly apply the d cube equal to minus a cube, right? So therefore first we have to split the d cube as d square into d, then apply d square equal to minus a square and then solve. And here if it is d cube we can apply d square, one d will be remaining in the denominator, then we need to rationalize the denominator to proceed further. That will come to know when we are solving the examples. So now here by using the successive differentiation, so d of sin ax, already we know that capital D is an operator and it is equal to d by dx. So therefore d by dx of sin ax is cos ax into a, that is a cos ax, then second order derivative d square sin ax equal to minus a square sin ax. So here sin ax is repeating after every even number of differentiation. So here also sin ax and here also sin ax, right? But on the first derivative here it is sin ax and it is cos ax. Now d cube sin ax is minus a cube cos ax. Now the function has changed. So therefore again differentiation, that will give d4 sin ax equal to a power 4 sin ax. So here that a power 4 can be written as minus a square whole square, because minus a square, its whole square is minus 1 square into a square, that is minus 1 square is plus 1 and a square is a power 4. So therefore, and here d power 4 can be written as d square whole square sin ax. So proceeding like this we will get here d square whole square is there, then for the sixth derivative that will become d square whole cube, and for the eighth derivative d square whole power 4, 10th derivative d square whole power 5, like that will become the multiple of 2 or even number. So therefore we are writing in general as d square whole power n sin ax equal to, and on RHS that is minus a square whole power n sin ax. So this is some standard result we got. Now from this The d square whole power n means that is a polynomial in d square or function of d square. So therefore that can be written as f of d square sin ax, and similarly here f of minus a square sin ax. So f of d square sin ax equal to f of minus a square sin ax. Now operating both sides by 1 by f of d square. So therefore this equation becomes 1 by f of d square into f of d square sin ax equal to 1 by f of d square into f of minus a square sin ax. So here we know that if f of d square is a operator, then 1 by f of d square is its inverse operator. So therefore operator and its inverse will get cancelled, then remaining sin ax is equal to 1 by f of d square into f of minus a square sin ax. So here sin ax equal to 1 by f of d square f of minus a square sin ax, and now dividing both sides by f of minus a square. So we get 1 divided by f of minus a square sin ax equal to 1 by f of d square f of minus a square divided by f of minus a square sin ax. So therefore this becomes 1 divided by f of d square sin ax is equal to 1 by f of minus a square sin ax. So here we have operated, or we have divided by f of minus a square. So therefore it implies that 1 by f of d square sin ax equal to 1 by f of minus a square sin ax, which is the required result. And now you can try this one. So try yourself. 1 by f of d square cos ax equal to 1 divided by f of minus a square cos ax if f of minus a square is not equal to 0. So this is also similar to the same, that sin ax. Here also you have to differentiate n times, you will get the result as same. Then after differentiation you have to use the inverse operator, then finally dividing by f of minus a square, you will get the required result. So prove this and upload in the Google Classroom. Now let us discuss some examples on the second case of particular integral. So the first example is solve d square plus d plus 1 into y is equal to sin 2x. d square plus d plus 1 into y is equal to sin 2x. So here in the previous case a is equal to what? A is the coefficient of x in the exponential function, and here a is equal to coefficient of x in sine function. So therefore here we can write that a is equal to 2 because it is sin 2x, hence it is a. So the auxiliary equation of this one is m square plus m plus 1 equal to 0. By solving the quadratic equation we get the results as m equal to minus 1 by 2 plus or minus I root 3 by 2. So by using the formula we have to find the roots. So it is a pair of complex roots and its complementary function is given by e power minus 1 by 2x c1 cos root 3 by 2x plus c2 sin root 3 by 2x. And now we should go for the particular integral. So whenever we are going to write the particular integral, the function of d must be right in the denominator. So here the function of d is d square plus d plus 1. Then it is 1 divided by d square plus d plus 1 and sin 2x. So in the previous example or in the previous case of the particular integral, just we have substituted d is equal to the value of a, but here we should apply only for d square, d power 4, d power 6 like that, or if any higher powers of 2 are there, then you have to split that power as multiple of 2 into some power of d. So now here d square, so we know that d square equal to minus a square. So therefore 1 divided by d square equal to minus a square means minus 2 square plus, we cannot put the value for d, so therefore d as it is plus 1 sin 2x. Now it is 1 divided by minus 2 square means minus 4 plus d plus 1 sin 2x. Then simplify the denominator. Here minus 4 plus 1 means minus 3, so that become d minus 3 sin 2x. Now the denominator becomes linear in d, means the power of d becomes 1. So whenever the power of d becomes 1, we cannot apply the condition, because it is applicable only if the power of d is more than 2, but here it is 1. So therefore in this case we need to rationalize the denominator. So already you know how to rationalize the denominator, multiplying and dividing by the term which is having the opposite sign of this denominator, that is d plus 3 divided by d plus 3 into d minus 3 sin 2x. Now it is d plus 3 and denominator becomes a plus b into a minus b, that is a square minus b square, then d square minus 9 sin 2x. Now look at the denominator. So in denominator we have d square, hence we can substitute the value for d square. So therefore it is d plus 3 divided by d square equal to what? Minus 2 square minus 9 sin 2x. So therefore here now it is equal to d plus 3 divided by, so minus 2 square means minus 4 minus 9 then sin 2x, it is equal to, here its value is minus 1 divided by 13 into d plus 3 sin 2x. So in our solution that d should not be remain, because we are solving that equation, means that variable should not be exist in our solution. So therefore it is minus 1 by 13. Now multiplying this, d into sin 2x plus 3 into sin 2x. What is d? That capital D is d by dx, right? So now d by dx of sin 2x equal to what? 2 cos 2x plus 3 sin 2x, which is the particular integral of the given equation. Then after finding the particular integral, you have to write the complete solution. So here y is equal to complementary function plus particular integral. So here it is the complementary function, that e power minus 1 by 2x c1 cos root 3 by 2x plus c2 sin root 3 by 2x, and the particular integral is minus 1 by 13 2 cos 2x plus 3 sin 2x. So therefore its complete solution is given by e power minus 1 by 2x c1 cos root 3 by 2x plus c2 sin root 3 by 2x minus 1 by 13 2 cos 2x plus 3 sin 2x, which is the required complete solution. So in this case you must remember that d square equal to minus a square. If after substituting that all the values, if any d is remaining in the denominator, in that case we need to rationalize the denominator and hence find the solution, and the d in numerator means that is the differentiation, the d by dx, or only if d is remaining then no problem, d is d by dx, then 1 by d is integration of x, but here it is not only d, it is a factor or it is a linear equation in d. So in this case we cannot integrate the function directly, so therefore first you have to rationalize the denominator and then move further. The next example is solve d power 4 plus 1 into y is equal to cos x. So here the auxiliary equation is m power 4 plus 1 equal to 0. So this equation cannot be solved directly, so therefore we have added and subtracted 2m square. So therefore it is m power 4 plus 2m square plus 1 minus 2m square equal to 0. Then by considering the first 3 terms, it can be written as m square plus 1 whole square minus 2m square can be written as root 2m whole square, and now it is in the form of a square minus b square, and a square minus b square equal to a plus b into a minus b. So therefore here m square plus root 2m plus 1 into m square minus root 2m plus 1 equal to 0. So these two are the factors of this equation, m power 4 plus 1 equal to 0. Now these two are quadratic in m, then separate these two, then solve. So the first term is m square plus root 2m plus 1. On solving this one, we get the roots as m equal to minus 1 by root 2 plus or minus I into 1 by root 2, and here m equal to 1 by root 2 plus or minus I into 1 by root 2. So the complementary function. So these are the two pair of complex roots. So in the first one, alpha equal to minus 1 by 2, beta equal to 1 by root 2, and alpha equal to plus 1 by root 2, beta equal to plus 1 by root 2. So therefore here e power minus 1 by root 2x c1 cos 1 by root 2x plus c2 sin 1 by root 2x, and for the second pair of the complex roots it is e power 1 by root 2x c3 cos 1 by root 2x plus c4 sin 1 by root 2x. So it is about the complementary function, and then particular integral is 1 divided by d power 4 plus 1 into cos x. So here it is cos x, means this is also similar to the previous case, that sin ax. Whenever sin ax is there, substituted d square equal to minus a square. Here also same, d square equal to minus a square. So now this is equal to 1 divided by, now d power 4 is there, the d power 4 can be written as d square into d square plus 1 cos x. So here a is equal to 1. Then 1 divided by, here it is minus 1 square plus 1 cos x, because d square equal to minus a square. Then 1 divided by, minus 1 square means minus 1 plus 1 cos x. 1 divided, minus into minus becomes plus, so 1 plus 1 is equal to 2 cos x. So therefore the particular integral is 1 by 2 cos x. Then the complete solution is y is equal to CF plus PI. So write this completely, complementary function along with the particular integral. The next example is d power 4 minus 2d square plus 1 into y is equal to cos x. So here also the value of a is equal to 1. The auxiliary equation of this one is m square minus 2m square plus 1 equal to 0. And here by looking at this one, we can easily say that it is quadratic in m power 4, and that is equal to m square minus 1 whole square equal to 0. So here it is square means there are two same factors, hence m square minus 1 equal to 0 and m square minus 1 equal to 0. So therefore m square equal to 1, m equal to plus or minus 1, here also m equal to plus or minus 1, then m take the values 1, 1, minus 1, minus 1. So therefore here complementary function 1 is repeated twice and minus 1 is repeated twice. So c1 plus c2x e power x plus c3 plus c4x e power minus x. And the particular integral is equal to 1 divided by d power 4 minus 2d square plus 1 cos x. So first split the higher powers of d as d square into d square minus 2d square plus 1 cos x. We know that d square equal to minus 1. So minus 1 into minus 1 into minus 2 into minus 1 plus 1 cos x. Here because d square equal to minus a square, so a is what? 1. Then minus 1 square which is equal to minus 1, that is d square. So therefore it is minus into minus becomes plus, so 1 minus into minus becomes plus 2 plus 1 cos x, it is 1 divided by 4 cos x. So that is the particular integral of the given differential equation. So here this is for the complete solution. Complete solution is y is equal to CF plus PI. So already we got the complementary function here, and this is the particular integral. Then sum up these two, then find the or write the complete solution of the given differential equation. The next example is d square minus 5d plus 6 into y is equal to sin 3x. So here a is equal to 3. The auxiliary equation of this one is given by m square minus 5m plus 6 equal to 0. Then m square minus 3m minus 2m plus 6 equal to 0. Then by factorizing this one, we will get m equal to 3 and 2. Hence these are the two real and distinct roots, and its complementary function is given by c1 e power 3x plus c2 e power 2x. Then the particular integral is equal to 1 divided by d square minus 5d plus 6 into sin 3x. So here we know that d square equal to minus a square, then it is minus as it is, a equal to 3 square, that is minus 9. So therefore 1 divided by minus 9 minus 5d plus 6 sin 3x, then 1 divided by, so minus 5d, then minus 9 minus 6, that becomes minus 3 sin 3x. So by taking that minus common, that we can write as minus 1 divided by 5d plus 3 sine 3x. So here look at the denominator. There it is a linear function of d. Whenever we are remaining with the linear function in d in denominator, then rationalize that to get the particular integral. So therefore here minus as it is. Now multiplying and dividing by 5d minus 3. So 5d minus 3 into 5d plus 3 sine 3x. This is equal to, by multiplying the negative sign to the numerator, that becomes 3 minus 5d into sine 3x, and denominator becomes a plus b into a minus b, where a is equal to 5d and b is equal to 9, means 25d square minus 9. So that is 25d square minus 9. Then this is equal to, so here this is equal to 3 minus 5d into sine 3x divided by 25. So already we know that d square is minus 9 minus 9. So here the denominator becomes 25 minus 9 minus 9, that will give the sum as minus 1 divided by 234. 25 into 9 is 225, then minus 9 is there, both are negative, so their sum is minus 1 divided by 234. Then in the numerator 3 into sine 3x minus 5 into d into sine 3x. So therefore minus 1 divided by 234. So this is sine 3x minus. So d of sine 3x means, or d into sine 3x means differential of sine 3x, that is 3 into cos 3x. So already 5 is there, so 5 into 3 becomes 15 cos 3x, or this is 1 divided by 234, the multiplying with negative sign, that becomes 15 cos 3x minus 3 sin 3x, which is the required particular integral. And do not forget to write the complete solution. Y is equal to complementary function plus a particular integral.